Hi, my name is Zachary Gonzalez, and I will be discussing my project in credit default analysis. I have a few words on the data set. So it's about the Taiwanese 2009 credit crisis. At the time, the economy was stagnant due to civil unrest. The objective is to train a model to predict client payments. This was because the financial industry wanted to know if they could be recouping the loans that they were giving out on a monthly basis. And we want to determine if the crisis is improving. The government was more so interested in the credit cards providing the credit card companies providing that information to the government. So we would also want to discern if there's an improvement or if it's getting worse. So we're going to be using a supervised binary classification for this data set. They either pay or they don't. Uh, it contains numerical and categorical financial information based on the client's history with the credit card company. And it also contains demographic features such as their age, sex, education, and marital status. And our overall goal is to focus on accuracy for the predictions, but we also want to discover actionable results for the credit card companies to utilize immediately. And since the demographic is being provided within the data set, I believe it's proper to include it with most of our analysis. Hmm. So the financial businesses want to be paid, so we're going to have to create a predictive model for them. But we also need to figure out from the business standpoint what they want, which I've already discussed. They're going to want actionable results, and they need to know if the economy is doing better. But we also need to understand the data, and we have to discern if the data is even good. We don't know necessarily if what they've collected is even going to help us with the response. It's a very human issue. Will they pay or not? And we have to discern which models are actually going to perform well in this environment. So the approach that I had originally was going to be using Python 3 with a TensorFlow for neural networks specifically, and I decided to use sklearn for decision trees. And now we have to go into how we're going to look at the data and how we want to input it into our model. Essentially, the observation selection strategy is the preemptive work that we're going to perform on the data before it goes into the model. After some extensive research, I realized that there were certain features that we want to exclude, or the values of those features. Others need a threshold because the outliers are so extreme that they skew all the results. And there's also a rebalancing issue or an imbalance issue with the class labels, specifically the class label of paying the next month. And we'll go into that in a few moments. So I'd like to discuss the features that we're going to have to remove because it caught me off guard. For the education, it specifically says that a value of 1 is graduate school, 2 is university, 3 is high school, 4 is others. But if you look down here on the bottom left, we have a value of 0, 4, 5, and 6. So originally I tried to discern what these values even meant. 0 could be a doctorate's, maybe. It could be something above it. But if 4 is other, what could 5 and 6 even be? So I decided to remove those. I don't know what they are. We can't provide actionable results for that. I don't even know who that would represent. And for the marital status, we have a 0, and that's the only one that actually exists. The 0.5, 1.5, 2.5 is because the x-axis needed the 6 ticks. It was the same function as education. But what would a marriage of 0 be? We already have married, single, and other. Other should cover everything else, so we're going to remove that value as well. Over here for the general data, the pay value over here, that represents delinquency for how many months out. So a pay value that has a value of -2, what does that mean? Because the researchers never actually described what that represents. For 0, it means they paid on time. 1 through 8 means they were that many months delinquent. So maybe a negative number means they're overpaid for that many months. But that doesn't really work out the way we would expect it to be, because we're about to be shown over here, there's a pay of -2 on both of these records here. And the pay 1 means it's the month before we're deciding if they're going to pay. So if they have overpaid by 2 months and they owe nothing, we have two different outcomes for this case, which means we can't even assume those are full months overpaid. We don't know what the negative values actually even represent. They never told us. Unfortunately, if we were to remove the negative values, we would hemorrhage around 4,000 records. So they are prominent. We need those ones. It's not like education where there are only a few. We also have to discuss the outliers. The outliers are surprisingly extreme, to the point where even when we would scale the data, they would skew the results. So we need to put thresholds on some of these. Unfortunately, we have to be extremely cautious with our thresholds, because someone who's an outlier for the limit balance might not be an outlier for the bill amount. So if we were to slice down here, we might be removing records within here, which is not something we want to actually do. So we're only going to be removing the extreme outliers for the extreme outliers, so the ones that are too far gone. So we'd be slicing down outliers that are isolated. Oh, my apologies on that one. So now we have to address the imbalancing issue. Out of 30,000 records, we've got 25% roughly that are in the does not pay the next month category, while 75% do pay their next month. And while this isn't exactly the worst for the neural network, because we can deal with that with our weights and things of that nature, unfortunately for the decision trees, this is going to cause significant issue, as once we get down to the leaf nodes, the majority wins the outcome. So we need to balance this. So I originally wanted to use random oversampling or SMOTE, but both of those actually were causing more issues by either oversampling the uh, based on sex, so the females are the majority in this data set, it would just mass produce female records. So I had to duplicate them by hand. I just took the does not pay category, duplicated them, and then the rest of the information I dealt with weights to finish off the balancing, while also maintaining the fact that they are the minority. We should be assuming people are going to pay. So now I'm actually going to talk about the decision trees. Ironically, the models were the easiest part of this entire project. The decision tree was very simple to create. It uses the tenfold cross-validation, but because of the cleaning of the data that we performed previously, where we were removing those extreme outliers, we were standardizing the data, we cleaned up the marriage and the external features, and with our hyperparameter tuning, with our leaf pruning, we ended up with an incredibly accurate classifier, especially for when we're classifying class 1. That is a very important one to be getting right. We want to know who's not paying their next month. So the decision tree did phenomenal. Unfortunately, the neural network was significantly more complicated to create. I originally had 4 models that I was making. 2 of them were slightly different variations of each other, while another 2 were using different methods of hyperparameter tuning. Ironically, the best model was one that didn't even use the hyperparameter tuning. I just got lucky with the initial results, because the hyperparameter one came up to the same conclusion. It performed best at 10 epochs, and it had an accuracy of around 73%. As you can see, the area under the curve is 79, it's bog standard for what other people have been getting, so I'm not very impressed with this one. But compared to the decision tree, you could see that it does not make that same misclassification where it's a person does not pay and we think they will. This one gets that wrong. And we could not get the recall value to actually increase, which I believe you could see with our confusion matrix. No matter what I did, that value wanted to plummet. So now I want to talk about some of the actionable insights that I was able to discover for these Taiwanese credit companies. So of all the does not pay next month records, before we did any upscaling, this is the true value. We've got 6,598 records of people who do not pay. The largest or the most common reoccurring demographic at 1,535 records were married females who graduated or are enrolled in a university. For this Taiwanese credit card company, they had a 23% chance of defaulting. Or rather, they made 23% of the defaults. That's significantly more than the other demographics. For example, if we just swap it to men who are married with a university degree, they were about 14% of all of the cases. Something experimental that I did out of pure curiosity was I wanted to discover the trends of people who do and do not pay. So I took the aggregation of the pay value or the pay amounts and the bill amounts of each month based on if they were in the does not or does pay classification. So over here on the left is the average trends of people who don't pay the next month. This is after removing extreme outliers, so this is more true to form. And I've also inverted these graphs. As you could see, it starts at value 6 and goes to value 1. That's because value 6 is September, and then it goes up. That's almost embarrassing. I don't remember my months off the top of the head. Either way, value 6 is several months ago, while value 1 is the immediate month prior to our classification decision. Anyway, as you can see, for people who don't pay the next month, their bill amount, which is in yellow, starts very high, and then it plummets. And then it stays fairly stagnant while essentially decreasing. Overall, they had a significant net loss on their bill amounts. And as you could see, their delinquency was also increasing in a pseudo proportion to what's going on with the bill amounts. But over here, for people who do pay the next month, you can actually see that it starts up high, drops down, goes back up, stagnates, drops down, goes back up, and they pay the next month. So what we can essentially discern from this, aside from the fact that the scales are different, this one goes to 0.25, this one goes to 0.4, what we could discern from this is that the people that are not paying the next month have either spent too much money and are catching up, or they do not have enough money to meet the bills that they've even created. Which I know that sounds like the same exact thing, but the dataset doesn't come with income, which would be very important to have. We only know if they were delinquent, and what we can assume is if they started this month with more delinquency, then they're going to be going over where they're paying less with even more delinquency, then they're not going to pay the next month, because over here we know they're going to pay the next month because they're paying more than they are delinquents. And that's just trends, so we could use that to essentially discern if someone's at risk. Not necessarily if they won't pay the next month, but if they follow the trend of someone who won't pay the next month. The model actually decides on if they do or do not pay. So now, in summary, I've shown that the decision trees actually outperform the neural networks for this classification problem, which is actually substantial purpose that I had for this project, the original researchers made a bold claim that only neural networks can classify this problem and that all other classifiers were significantly inferior. I've also created a diverse framework in Python to handle these classifications, specifically on the business results aspect, where it'll tell you what the trends are, how the people are performing, who's going to be the most at-risk demographic, and things of that following nature. And I've personally learned about several topics. I've learned how to work with TensorFlow and GPU utilization for neural networks. I've learned how to work with financial investigation as and anomaly detection, as I had to discern what pay -2 meant, if people who were overpaid on their previous bill wouldn't be paying the next month, and things of that nature. It was a lot of financial nuance. And I discovered and learned about real world solutions to actual problems. This is applicable to the real world. I can apply this to another financial institution and come up with results. And some of the future work that would be done on my work specifically is to actually analyze the distribution of the predictions that were coming out to discern if the economy is going to be doing better over the long run. Considering the poverty rate of Taiwan was at 20% and our does not pay the next month classifications were at 25%, it's safe to say that at that given point in time, the economy was not doing better. And we'd also be wanting to acquire income features for the next future datasets. Having a client's income is extremely important to determining if they're going to pay or not. I feel like knowing what job they have is also pretty good to know, because you could assume their pay range with just their job. You don't need to have that kind of personal information if you don't want to collect it. Either way, something else that could be done is the testing of different hyperparameters, such as the early stop and loss decay for the neural networks. I will absolutely admit I was out of my league with the loss decay. I did not figure out how to get that one operational. I did have an early stop, but every time I was using early stop, it kept increasing the cost of running the epochs, and it was just slowing down the machine, and I did not have 9 years to actually process everything. I was not very exhaustive for the neural networks as much as I would have liked to be. And also, testing of the ensemble methods would be pretty lucrative, in my opinion. Considering that the decision tree was extremely accurate with just some data cleaning, having an ensemble method with bagging would honestly increase the results. It would be looking at more combinations of features. It would be removing sex from the equation for some of them and figure out something new on if that target would pay or not. And I believe that's something that should be done and looked into. And some of the references, the primary reference is actually the paper that this was all based off of, where everyone got the information and was working off of. I obviously got it from Kaggle, but I read their paper, I looked at their data set, and I got all my information from them. Anyway, thank you. I'm Zachary Gonzalez. You could contact me at that email on screen. This was for the New Jersey Institute of Technology, CS482. Thank you, and have a good day.